I'm glad to present to you today part of my verification and validation process that I did during my PhD. I'd like to thank the organizers for organizing this workshop because in my experience as a PhD student, I found that often papers and scientific journals put a lot of emphasis on the presentation of extraordinary claims and novel computational physics, and very little attention to the verification and validation process, at least in the Lattice-Boltzmann method that I used for the simulation of rarefied regimes. So I'll introduce first what was the motivation for all this research. It was the filtration of the removal of airborne particles from air. So here are some examples of harmful airborne particles like photochemical smog that I show here. Then there is also dust in workplaces, and I don't have to talk to you about bacteria and viruses. So we often use facial masks, such as the N95 mask that I show here. And often those air filters are designed by trial and error. And theoretical understanding is lagging behind fabrication processes improvement. So for example, it is widely known that using nanofibers in conjunction with microfibers leads to more efficient filter design. But whether it is better to put the nanofibers in layers or to put them well mixed in microfibers, as in this geometry, is still a matter of debate. And one of the reasons for this is that flows around nanofibers are in the rarefied regime. Here I show what I mean by a rarefied flow. So actually this is a continuum regime flow. So when the pore size is relatively large, like larger than 100 microns, air can be considered as a continuum. That means that if I zoom, the properties of the fluid don't change. They always stay the same. And the fluid can be modeled with the Navier-Stokes equation with a zero velocity boundary condition. At 10 microns, however, a finite slip velocity appears at the boundaries of the pore, which must be included in the model. At around 100 nanometers, the fluid can no longer be considered a continuum, and we call this the transition or Knudsen regime. However, like in that case, the interactions between gas molecules are not negligible either. But if we go to like 1 nanometer pore size, the interactions between gas molecules themselves are negligible, and the regime is called a free molecular flow. So slip flows at the boundaries must be taken into account in the rarefied regimes. Let us first consider a flow between two plates where the mean free path lambda is large. A flow is established with a maximum flow reached in the middle, and the macroscopic velocity is the sum of the contributions of all molecules in the control volume. And because the mean free path is large, the contribution from the middle creates the non-zero slip velocity. And one successful model that was proposed in the literature for slip is a second-order Maxwell boundary condition, where the value of the slip velocity is a function of first and second order derivative in the velocity at the surface and the effective mean free path of gas molecules near the solid surface. So here I'm going to present to you like the Lattice-Boltzmann method. It is an alternative CFD paradigm to solve Navier-Stokes equation. So usually with the continuum mechanics assumption, a momentum balance is derived for a fluid element. Then it is discretized with a finite element, finite difference, or a finite volume method, and the flow field is recovered through solving usually an implicit scheme by solving a matrix equation. And then we recover the flow field. The Lattice-Boltzmann method, however, starts by discretizing the Boltzmann equation here, which has 3 dimensions in space and 3 dimensions in velocity. So it's a statistical mechanics approach. So first, there is a discretization in the velocity space and then in space and time. With a later integration in velocity space and with the assumption of Mach being smaller than 1 and Knudsen being smaller than 0.01, the same flow field as the Navier-Stokes equation is recovered. And the main advantage of the Lattice-Boltzmann method for the simulation of flows through porous media is that it is highly parallelizable. So as we can see, all of those operations are local and for each node, which makes it easy to distribute computations on many CPUs. So how do we set fluid properties with the LBM, such as viscosity? In the continuum regime with the LBM, the viscosity is set as equal to the pressure times the relaxation time shifted by 1/2 and the time step that is chosen. But from kinetic theory, we know that the mean free path is related to viscosity, pressure, and temperature in the following manner. And usually, temperature stays relatively constant in the domain. And recalling like the definition of the Knudsen number, that is the ratio of the mean free path to the characteristic length of the geometry, we know that as long as the Knudsen number is below 0.01, the Navier-Stokes equations are recovered. So the actual value of the mean free path does not matter to recover Navier-Stokes equation without slip. And so we usually set tau equals 1 and in the continuum regime for that reason. However, in the slip regime, so I recall the slip model that I presented to you earlier from Joe, where the slip velocity is a function of the mean free path and the mean free path squares. And this means that the mean free path in the rarefied regime, the slip regime, is a physical value and cannot be neglected. Thus, the relaxation time tau is fixed in the slip regime in the following manner, where we have tau that is that depends on the mean free path, and it also depends on the grid size, delta x. So we see that relaxation time increases with grid size refinement in the rarefied regime scheme. So let's compare convergence order between conventional CFD solvers and the LBM. So in conventional CFD approaches, generally, spatial and temporal discretization determine the convergence order. And imposing a slip boundary condition is relatively straightforward. Compared with the LBM, as a Navier-Stokes solver in the continuum regime, we have that for commonly used velocity discretization, the D2Q9 scheme that I present here, the explicit Euler discretization gives a second order convergence in space and time. That's a commonly known result. But we also know that boundary conditions can degrade the convergence order. For example, if I have a non-planar geometry like this, it's known that if the boundary condition is not properly set, that you can have a degradation of the convergence order. And typically, the convergence order is evaluated with a fixed tau that is equal to 1, as I explained earlier. But in rarefied flows, tau is equal to 1/2 plus a constant times the mean free path divided by the grid size. So, well, all those elements have left some confusion in the literature, even I would say a controversy on the convergence order of the LBM in the rarefied regimes. So for a gas flow through a slit in the slip regime that I present here, there has been some controversy in the literature. For example, Guo, Zheng, and Shi, for an incompressible scheme, they say that the order of convergence is 2. However, Kim, Pitch, and Boyd in 2008 for an incompressible flow said that the order of convergence should be 1. And Verhaeghe, Liu, and Pince for a compressible flow said that the order of convergence should be 1, but they attributed the degradation of their scheme to the compressibility of the problem that they solved. So what is the actual source of this discrepancy? We need to investigate this before tackling non-planar geometries, as I said, because sometimes there is degradation of the convergence order when there is non-planar flows, non-planar geometries. So we need to decouple the geometry-related errors from scheme errors. And my hypothesis that I brought forward was that the relaxation rate might be the cause of the controversy. So I presented a test case, an incompressible gas flow through a slit, so I made sure to remove the compressible effect. So we have this incompressible slip flow between two infinite planes. And first we setted the continuum regime with tau equals 1, and we saw that we recovered second order, a convergence order for the traditional continuum regime flow with the LBM. And this is nothing new, but it is an essential step of our verification procedure. Because if we recover something else, then it has the code that has trouble, not the scheme. So we see that when we impose a slip flow with a fixed Knudsen number of 1, which is well into the rarefied regime, we see that we have a degradation of the convergence order, where rather than having second order convergence, we now have first order convergence. And this appears rather disappointing, and it might have solved the controversy, but it's actually more complicated than that. So we see that when we have a slip flow with a fixed relaxation time of tau equals 1, note that, however, in this case, each of the points that is traced does not correspond to the same physical problem. So we have that the Knudsen number changes for each of the points. However, we see that when we use the similar metrics to the ones used before for the continuum regime, the same convergence order is recovered. So the slip boundary condition is not per se the cause for the degradation in convergence order, as some have theorized, like for compressible flows, but it is the increase in relaxation rate with the refinement of the grid. So in conclusion, so we have investigated the controversy regarding the convergence of the LBM in the rarefied regimes. We have recovered the second order convergence in the continuum regime for the code. So we verified that the code works. For a fixed Knudsen number, a first order convergence is recovered. But for a fixed tau, a second order convergence is recovered in the slip regime. And we have shown that the apparent degradation in convergence order is caused by the increased relaxation time as we refine the grid. So when we have the delta x goes to 0, the relaxation time increases to infinity. And this is what actually causes the degradation in the convergence order. So I'd like to thank the GPS and the NSERC for FONSAFE for the grant that they gave me during my PhD. And I know that well, this is a cute result that I presented, but I know it's very technical in nature. So we have like 2 minutes for questions, and